So today I'm going to talk about my research, non-progressive diffusion on social networks. So it is a joint work with Zhang from SU, Renyu from CHK, and also my advisor, Shen. So basically, we are considering about like some product or like some services that will have utility that is not only depend on the users themselves. So basically, for example, this called teleparty service, it emerged from like the pandemic years, like people cannot hang out like with their friends to watch a movie. So like this kind of service provides a chance that can synchronize all of the feedbacks and the real-time actions from different users so that they can also kind of enjoy watching the movie at the same time with their friends, even they are not meet each other in person. So for example, this kind of services, we will see like the utility of whether people would like to choose to use it will not only depend on their own preferences, but also may change because of the influence of their neighbors or friends or like their recommendations or whether they will engage also in this kind of services. So in this work, we call it non-progressive diffusion because we also allow the users to reverse their decisions as time evolves. So from the operational side, like for the platforms that would like to run this kind of services, they will consider some different decisions. For example, how to price the services when considering such kind of diffusion, or we can also use like the network externality to say about this kind of services and how we can select users for promoting a new service. So that will be some typical problems that will be considered. So in this work, I guess it does not include the animation also. I will maybe still change back to the PowerPoint, but so I will try to edit it. So basically there are two different streams of literature. So basically I will just like get rid of this kind of slide and try to make the point clear. So basically there are two different streams of literature. One might basically comes from the sales community and the other from like the economics or like operations management community. So for these two different streams of literature, there are some fundamental problems here. So one of the problems is like how we can balance between the precision and the efficiency. So first of all, like the first stream that comes from the CS literature, they will mainly use some micro-founding models which can capture all of the complex dynamics so that they can quite accurately mimic the diffusion processes. But this kind of model, the problem is like, if we want to evaluate the diffusion influence, like we may need to use the simulation techniques. So that is the only way we can get the total inference from this entire diffusion. So that if we want to like solve the operational problems, we also need to use simulation optimization, which is quite time consuming. But the other stream of literature, like mainly comes from the econ or OM fields. Like for example, the mass diffusion model or like the network game models, like people will use kind of micro-founding models so that people will focusing more on the equivalent side. These kind of problems can be solved more efficiently, but sometimes it loses the like the precision when we want to characterize this entire dynamics. And this kind of model will also be criticized about these problems. So in our work, what we want to do is kind of to bridge these two different streams of literature. And here we say like to balance between the precision and efficiency. And so in today's talk, I will mainly introduce 4 parts. First of all, like how we model problem, and then what is the theoretical results, and how it can form in practice, and finally how we can use this kind of scheme in the real-world operational applications. And for the modeling part, we will start from our micro-founding models, which comes from the first stream of literature, and to show what is the gap between the like the equivalent style of work. So basically, let's consider we have a social network. here we have a set of users. Each of them have their own intrinsic utility. What we see, we have the social networks that we have a certain kind of links, arrows between different users, which means like here, the arrow from user K to user I means like user I follows user K, so that user K's activity will also affect user I's utility when they want to choose whether to adopt the service or not. So that the choice model here we use like for each of the user, the adoption utility comes from 3 different parts. The first part is the intrinsic utility, which is independent of others. And the second part will be a network effect term, or like the network externality. Beta here is the network effect intensity. And the Y will be the adoption status, which here we use a binary random variable to denote whether their neighbors have already choose to use this kind of service or not. And also the error term will be the random noise. And at each of these time, the user will choose to adopt it if the entire utility is greater than 0. So that we can see like here we will embed the entire network effect given any kind of arbitrary network structure. For example, the user I, the network effect will comes from for 2 neighbors, which here we also normalize it using the in degree, which is the number of in neighbors here. And similarly for user J, the network effect comes from I, and for user K, the network effect comes from user J, which depicts how the network effect influence the entire diffusion. But of course, this model here will be at each of the time step. But when time evolves, because of the actions of each user will also become different, so that the network effect will also spread across the entire network. So that means like the distantly connected neighbors will also have impact on the specific users, but only after certain time periods. So we can see, first of all, this model, like we do not have any assumption on the network structures and also the noise distribution. And it can be related to the random utility choice models and also like the classical diffusion models, which I've mentioned before, like in the first stream of literature. So which characterize all of the stochasticities, include the entire network specifications into the model here. So then, like for the platform, like what's their objective? Because they want to make some decisions. So first of all, they want to know like the kind of the long-term limiting behavior of each users under this kind of model. So what they want to evaluate is like the expectation of the adoption states here, or like in other words, the adoption rates for each of the users. A simple way to calculate all of these things is like to use a Markov chain. For example, still use this 3-node network as an example. Because of our definition, we can construct a Markov chain. But as we can see, the state space of this Markov chain will be the combination of all of the adoption states, which will be in total 2 to the power of n, which is exponential to the network structure. So that if we want to construct such a Markov chain, or even like to calculate the stationary limiting distribution of this Markov chain, will be prohibited even for a moderate size of the network. So what we do is like for the Markov chain, like if we can write out the so Q here denotes the adoption probability. If we can write out the entire explicit expression here, it will be looks like this. The only problem is like we cannot calculate this expectation of over an arbitrary CDI function of this with the random variable y here. So what we do is like to we try to use a deterministic variable mu here to approximate these entire things. Or in other ways, so if you are more familiar with the network games, those equivalent things, you can look at this fixed point approximation. It's just like some definition of the network games models. So here, if in any case we say we can show like this mu is indeed close to the final result of this Q, then like for some kind of network, we can provide such kind of justification that these kind of network game models will be already sufficient to characterize about the network diffusion here. So like all of our following work will be quantify the gap between these Q star and mu scales. And the key technical challenge here is because like this Y is because of the adoption states, which will have no like independent assumptions, and this correlation is not like defined by us, but like it will evolve across the time horizon and also the entire network structure. And also because we have an arbitrary, like we have no assumptions on the noise distribution, so the CDI function will be like nonlinear. So in the next part, I will talk about some bounds on this gap between Q star and mu star and based on the network structures. So this will be our major results. So here we use this absolute value notation to denote like the entry-wise absolute value. So that is for each of the user R within the network, we calculate the absolute difference between Q star and mu star. We show that it can be upper bounded by a novel metric we propose here called the inverse in degree centrality. So basically, this metric just characterizes the connectedness of each user within the network. So how does this metric comes out? So basically, first of all, it will depend on what we call the independence discount parameter, which is determined by both the beta, the diffusion intensity, and also the distribution of noise. Or in other way, you can interpret it as the sensitivity to both the network effect and also the randomness effect. And then this entire centrality will be a summation over infinite terms. So the first term, it will only be related to themselves, which will be just the inverse of the in degree of the user like themselves. And then the second term here will include some information from their neighbors, like from their one-hop neighbors that is directly connected to them, which will include the inverse in degree from their neighbors. And so on and so forth. All of the following term will be a kind of discounted inverse in degree from more distantly connected neighbors. And the good thing is like this summation can be kind of have a closed form expression here, and it will be takes the form of the inverse of the matrix times vector. So if we are familiar with like the network literature, we know like there are some kind of centrality terms. For example, this Bonasich centrality. It also takes the same forms. But the difference here is that this kind of Bonasich centrality is like proposed directly to denote about the importance of each of the agents within the network. But here we arrive at this inverse in degree centrality just by derive all of the mathematical things. So it naturally like derive something that some different centrality metrics that can also characterize about the difference between Q star and mu star. So to be like a general framework here is like, because previously we have two different challenges. So what we do is like at the first step, we bound the correlation of this random variable y here. And what we use is just the centrality measure there. And then when we bound the second step, the nonlinear transition, we just propose two auxiliary fixed point iterations. So it can be also bounded the entire trajectory of Q and mu. And here, the centrality can offer some insights into how the stochasticity is disseminated. To help us to understand this entire, like what kind of network might have better approximation by mu, like we also derive the L infinite norm on the difference between Q star and mu star. So here we can see we can use the another metric, the minimum in degree D mean to denote about these upper bounds. So if we can like to imagine like, although this is a loose bound, it tells like if a network becomes much larger or much denser, then the approximation will be better. So recall that while we want to use kind of approximation or like what kind of under what kind of situation network this approximation might be more useful or more efficient. It's just those who are like cumbersome to do simulation, which will just be the large and dense networks. So that means like if in reality we encounter this kind of networks, it will be good to just use the network gain models, and we can already have quite accurate results. Like previously, we have these two different metrics, but two of these also have their own advantages and disadvantages. For the centrality one, although like we have a closed form, but it still involves the inverse of a matrix, so that it will still be kind of the calculation will be inefficient, and this minimum in degree, of course, will be overly conservative and might be vulnerable to outliers. So we also provide this L1 norm, which use inverse in degree density, which just be the average of the in degree of over all of the users here, which can be calculated much faster, and also help us to characterize the entire network structure here. So then we will look at some numerical experiments. So we calculate both the Q star and mu star on different networks. First of all, we use an example, 10-node example simple network as here. Like here, we use the size of each node to denote the exact arrow. So much larger means like the approximation is worse. So what we can see is like for the nodes that have fewer neighbors, the approximation seems worse here. We also like compare this exact approximation arrow with the centrality here in the right figure. We can see it almost have a perfect correlation, because previously what we provide is only an upper bound, but how this upper bound relates to the exact arrow here is unknown. But the numerical here seems like it performs quite good. And we then also perform this on some real-world networks. We use some Facebook network to show the results. And here we can see, first of all, if we look at these values here, among all of the networks we tried, that the worst made for the approximation error will be only 3.48. So although like it seems like in our program we say like it will be much more useful in the large and dense networks, and people will be curious like in real world whether the network is already dense enough or not. So like on this kind of real world network, we can see like this kind of social network, online social network has already has some really accurate results for this kind of network. And we also compare it with the other density metric we have here. We can also see like these blue dots denotes the map of the real world network, and the other dots like the triangles will be some synthetic networks. We can see it also have a full positive correlation here. So that will say like this kind of metric will also be quite useful. And in terms of the efficiency, we can see that we calculate this mu instead of the Q will have around 70 to 230 times improvement in the calculation time. So finally, I will move quickly into the operations problems. So one of the most common problems like the inference maximization, we want to find a subset of seed users from large networks so that can maximize the total inference. So originally, like if we can see like the inference maximization, like they will not have an explicit optimization form. Like we will say if the entire distribution follows such a dynamics, we can use simulation to calculate about the final total inference. But if we change it into like use this approximation to formulate this optimization problem, we can use this fixed point as the constraint, just as some like game optimization models, so that we only need to solve these approximate formulations. So I will not describe this entire our algorithm to solve this inference maximization problem. So what we compare is like, first of all, we compare it with the simulation optimization algorithm, which is the line like the lower line, so which is almost comparable with the simulation optimization algorithm. But also we consider like, because of the simulation optimization, if we want to gain high accuracy, we just need to like take longer time to get sufficient samples there. What if we just truncate it at some point to make it more efficient, but with relatively low resolution? We also compared with this FBA-induced algorithm, we can see there's a significant degradation here. So that will be like the main usage of this kind of framework. So that will be the main content for this work. Mainly, I just try to bridge between two streams of literature and show like this kind of approximation scheme can be applied to general cases like general network structures and also very general operations problem, not only just restricted in the inference maximization problem. So that's all. Thank you for your attention.